Hi, gang. Day 4. Let's see. You guys are probably still all sleeping. It's about 7:30 in the morning, Thursday. Let's see. Okay. Well, let's approach this the same way we have the other ones. Notice I have a -2 tangent squared of x and a -1 tangent squared of x. So they certainly appear to be similar. So I'm going to move this guy over to the right so that I get a positive coefficient. So that means I'm going to have to move the constants over to the left. So let's see, that will give me a tangent squared of x equals 9 minus 6 is 3. Okay, so I take the square roots, and don't forget I've got 2 square roots. Okay, so I get tangent of x equals plus or minus radical 3. Okay, and so let's see. I've got to worry about tangent of x equals radical 3, and I've got to worry about tangent of x equals the opposite of radical 3. Okay, so let's go to our unit circle. And if we take a look in here, let's suppose we just look in quadrant 1. Okay, well, we know the tangent is going to be 1 here at pi over 4. So tangent being radical 3 has to happen at either pi over 6 or pi over 3. Okay, so we've got to take a look at, okay, well, let's see. Tangent of x is equal to sine of x over cosine of x. And on the unit circle, that would be y over x. Y over x. So why don't we take a look at pi over 6 and see what happens there. Okay, so my coordinates are radical 3 over 2 and 1/2. Okay, so I would have to go tangent, okay, would be 1/2 over radical 3 over 2, which would give us 1/2 times 2 over radical 3. And notice that won't give me radical 3, that'll give me 1 over radical 3. So this is a big no right here. It doesn't work at pi over 6. So hopefully it works here at pi over 3. Okay, so let's check at pi over 3. Okay, so let's see, pi over 3, I've got coordinates 1/2 and radical 3 over 2. So again, tangent would be on the unit circle would be y over x as a sine over cosine. Okay, so I'm looking at that guy and I go, okay, let's go radical 3 over 2 divided by 1/2, and that would give me radical 3 over 2 times 2 over 1. So notice they cancel and it gives me radical 3. Okay, so the tangent of x would be equal to radical 3 at pi over 3. Okay. Okay, so let's see. Where else would it be equal to radical 3? Well, it would have to have these same coordinates, 1/2 as the x coordinate and radical 3 over 2 is the y coordinate, but I've got to make sure it gives me a positive radical 3, so either they're both positive or they're both negative down here at 4 pi over 3. Okay, so that would also happen at 4 pi over 3. Okay, so let's see, well, when will we get tangent of x equal to negative radical 3? Well, again, it goes back to what happened here at pi over 3. We know we have to have 1/2 as the x coordinate and radical 3 over 2 is the y coordinate to get radical 3, but I need the opposite of, so 1 has to be negative, 1 has to be positive. So if we go here to 2 pi over 3, notice I would get a positive divided by a negative, which would give me a negative, and I know I'm going to get radical 3 when I do that. So okay, this happens at 2 pi over 3. Okay, and then where else? Well, it can't happen down here because they're both negative. So a negative over negative is a positive, so it has to happen over here. And let's see, I need 1/2 and radical 3 over 2, and one of them has to be negative, so that would happen at 5 pi over 3 right here. X equals 5 pi over 3. Okay. All right, so we have everything we need to work on our solutions. Okay, so again, let's go from 0 to 2 pi. And obviously I have 4 solutions there. Okay, I've got x equals pi over 3. I've got x equals 4 pi over 3. I've got x equals 2 pi over 3. And I have x equals 5 pi over 3. And obviously it doesn't matter which order you put them in. Okay, and then if I go the set of real numbers, okay, I'm going to get x equals pi over 3 plus 2n pi. Okay, I could say x equals 4 pi over 3 plus 2n pi. Okay, I could say x equals 2 pi over 3 plus 2n pi. And I could say x equals 5 pi over 3 plus 2n pi, okay, where obviously n is an integer. Okay, and that's certainly one way to do it. Notice that you, technically you could combine these two, because if I add pi to pi over 3, that'll give me 4 pi over 3, so I could combine these two if I wanted to. Okay, just like this, guys. And I'm not saying you have to do this, I'm saying it's just another way to do it. I could say x equals pi over 3 plus n pi, okay, where n is an integer. And so I could start at pi over 3 and add multiples of pi, not even multiples of pi, all multiples of pi, because if I look there, I go, pi over 3 plus pi gives me 4 pi over 3. Okay, so I could do that. I could actually do the same thing here if I wanted to. I could combine these two, because notice, if I take 2 pi over 3 and add pi, I get 5 pi over 3, so I could say x equals 2 pi over 3 plus n pi, where n is an integer. So it's just another way. And that comes back to, you know, right here, we're using from 0 to 2 pi like we do with sine and cosine, so I'm kind of setting it up going along those lines, but technically a period of pi just goes from 0 to pi, not 0 to 2 pi. Okay, so you know, this guy is generated by adding pi to pi over 3, and this guy is generating by adding pi to 2 pi over 3. So it's just a matter of how you want to represent them. Okay, you know, if you want to stay consistent, you just stay with this stuff here. If you want to play around with it, there are multiple ways to represent your answer. And so we're in good shape there. Okay. All right, let's see what we got going on here. All right, this guy looks a little bit different than the ones we've been doing. Okay, because notice I have a cosine squared and a cosine to the first power. Okay, and so obviously they're not similar. Okay, so a lot of times when you see this, the first thing that you should consider is, could I put this in some sort of standard form, like I would with a quadratic equation, and solve it by factoring? And we say, okay, well, maybe we can do that. So if I'm going to put it in some sort of standard form, I'm going to put everything over to the left and set it equal to 0, and then see if I can factor it using factoring patterns I already know. So I'm just going to bring this guy over here like that. Okay, so let's see, we would have cosine squared of x minus 4 cosine of x plus 3 equals 0. And notice it's kind of like a quadratic, because we have something to the second power, something to the first power, and then a constant. And so I say, okay, well, maybe it'll factor, you know, like a quadratic. All right, now notice there's only one way to split up cosine squared of x, and that's cosine and cosine. Okay, so cosine x and cosine x. Notice the constant term is positive, so these two signs here and here have to be the same. They both have to be negative, so it'd be cosine minus and cosine minus. And then notice the leading coefficient is 1, so all I have to do is say, okay, what are the factors of 3 that add up to 4? But that's 3 and 1. And it factors like a quadratic. Okay, so we solve it just like a quadratic. You say, okay, well, if this is the case, if this whole thing is equal to 0, then either this guy is equal to 0 or that guy is equal to 0, one or the other. Okay, so cosine of x minus 3 equals 0, or cosine of x minus 1 equals 0. Okay, so this would mean that the cosine of x equals 3. Now that's impossible, okay? The reason being is that the range of sine and cosine, both of them, okay, goes from -1 to +1 along the y-axis. So there's no way that the cosine of anything could be equal to 3 because that's not in that range. Okay, so that's a big no. Okay, this is no solution. Okay, and you can see that on the unit circle. Okay, if you go to the unit circle and you say, okay, well, cosine are all my x-coordinates. Well, if you go around and look at all your x-coordinates, okay, the largest they ever get is 1, okay, all the way around, and the smallest they ever get is -1 all the way around. Okay, so all of your x-coordinates are in between -1 and 1, so how could cosine be equal to 3? That's impossible. Okay, so this guy, we solve this and we get cosine of x equals 1. Okay, so we say, okay, well, when is cosine of x equal to 1? Well, we go to our unit circle. When is the x-coordinate equal to 1? Because obviously cosine is the x-coordinate. That happens at 0 or 2 pi. Just a matter of, what you want to call it, 0 or 2 pi. Okay, but it doesn't happen anywhere else all the way around. So we only have one solution, x equals 0. Okay, so on our single period from 0 to 2 pi, we have one solution, x equals 0. Okay, and let's see, our solutions on the set of real numbers then would be x equals 0 plus 2n pi, where n is an integer. And obviously the 0 just goes away, so we just say, okay, the better way of writing that, okay, the best way of writing that would just be x equals 2n pi, where n is an integer. Okay, we got everything we need. Okay, that guy's down. How about we try a similar type problem with sine? Okay, notice very similar to the last one where we have sine to the second power, sine to the first power. Obviously, they're not similar. So we say, okay, well, let's put it in some sort of standard form. So let's gather everything on one side. And obviously, I'm going to gather on the left-hand side because sine squared is positive on the left-hand side. And just set it equal to 0 and see what we can do. So this guy is going to come over, okay, and this guy is going to come over. Okay, so I'm going to get sine squared of x. This becomes positive for sine of x, and this becomes -5. Okay, again, let's see if we can factor it like a quadratic. Only one way to split up sine squared, that'd be sine times sine. Okay, the last term is negative, so that means the signs have to be different. So one has to be positive, one has to be negative. The leading coefficient is 1, so I can say, okay, what are the factors of -5 that add up to 4? Okay, well, that would be +5 and -1. Okay, so if we multiply these two together and it equals 0, either the first binomial is 0 or the second binomial is 0. So we get sine of x plus 5 equals 0, or sine of x minus 1 equals 0. All right, so to solve this one, we would get sine of x equals negative 5. And just like the last one, when we consider the range of sine and cosine, we know that both of them go from -1 to +1. So it's impossible for a sine of some angle measure ever to be -5 because that's not in that range. Okay, so that gives us no solution. Right there. Over here we get sine of x equals 1, and of course that would work out. So we go to our unit circle and we say, okay, well, sine is our y-coordinate. 1 is our y-coordinate equal to 1. Well, that only happens up here, okay, at pi over 2. That's it. Nowhere else does it happen. So we only have one solution. Okay, x equals pi over 2. Okay, so from 0 to 2 pi, we just have one solution. X equals pi over 2. And then in the set of real numbers, we just keep adding even multiples of pi. So it would be x equals pi over 2 plus 2n pi, where n is an integer. Okay, easy enough. Okay, I ran across a problem yesterday. It's not in your notes, but I thought we ought to take a look at it. And it's very similar to the last two we did, but not exactly the same. Okay, kind of cool. Okay, I want to say I think there's a problem similar to this on the quiz. Okay, but notice again, I have cosine to the fourth and cosine squared, so obviously they're not similar. Okay, but notice I have this degree 4, which we didn't see in the last two. But what if we try putting it in some sort of standard form just like the last two and see what happens? So we got cosine to the fourth of x plus cosine squared of x. Move the 2 over so it becomes negative. And we say, okay, how about we try factoring? Okay, so if we consider our factoring patterns, remember with quadratics, okay, if you have an x squared term, we always split it up as x to the first and x to the first. Okay, so it makes sense here that if we have a fourth degree, we would split it up as x squared and x squared. Okay, so why not go this route? Go cosine squared of x and cosine squared of x. Now, the good thing about that is notice that when we use the FOIL method here, our O's and I's will be cosine squared, which we have. Okay, so we look here. The last term's negative, so that means one of these guys has to be plus, one has to be minus. And so I just asked myself, what are the factors of -2 that add up to +1? Well, that obviously would be +2 and -1. Okay, so it does factor. Okay, so this is cool. Okay, so let's see. So we could get cosine squared of x plus 2 equals 0, or we could get cosine squared of x minus 1 equals 0. Okay, so this would be cosine squared of x equals -2, which is impossible. Okay, in the set of real numbers. Okay, you would have to bump over to the set of complex numbers because you figure if this is the case, we would get cosine of x equals plus or minus the square root of -2. So in the set of real numbers where we're working, there is no solution here. Okay, so that one gets thrown out. This guy, let's see, we're going to get cosine squared of x equals 1. So taking the positive and negative square roots, this would give us cosine of x equals plus or minus 1. Okay, so we go to our unit circle, and that works. And we say, okay, well, you know, what's going on here? X equals, well, when is the cosine equal to either positive or -1? Well, cosine is our x-coordinate. So cosine is +1 at 0, and it's -1 at pi. And those are the only times that it's either 1 or -1. Okay, so we get two solutions here. x equals 0, and x equals pi. Okay, so let's see. From 0 to 2 pi, we have two solutions, x equals 0, x equals pi. Okay, and then let's see, on the set of real numbers, that would be x equals 0 plus 2n pi, and x equals pi plus 2n pi, okay, where n is an integer. Now, this is certainly one way to do it, okay, but notice that we could probably play around with this a little bit, because you figure here 2n pi, 0 plus 2n pi is just 2n pi. So if n's an integer, 2n pi represents all of the even multiples of pi. Then down here, that would be an even multiple of pi plus pi, so this would represent all the odd multiples of pi. So another way to kind of sort of combine these guys is just saying, okay, well, x equals n pi, where n is an integer. Okay, and so that takes care of every single multiple of pi, both even and odd. Okay, so again, there's nothing wrong with this up here. It's probably not the best way to do it. This is probably the best way to do it, okay, in all truthfulness, but, you know, this would certainly be okay. All right, and that wraps it up for the week. If you didn't notice, I posted a quiz yesterday, so that's due next Monday. And you guys let me know if you need any help with anything. You know, shoot me an email or get in touch with me through Google Classroom. We'll get you squared away. Miss you guys.